Hello students, in this module we are going to discuss definite integral and area between curves. Okay, so in last module we have learned integration as a reverse process of differentiation, that is indefinite integration, and we will be linking that indefinite integration in definite integration, how to solve definite integration using that technique. So if we say integral fx from a to b, here we say from a to b dx. What does it mean? This is called definite integral. Definite integral of fx from x is equal to a to x is equal to b. From x is equal to a to x is equal to b. This means that fx, suppose this is the curve y is equal to fx, and we have point x is equal to a here and x is equal to b here. So what is the area between curve and x axis? So this area represents the value of this integral. So this integral represents a value, gives a value, which is nothing but area bounded by line x is equal to a, x is equal to b, the curve and the x axis. Okay. So we can have definite integration limit of sum. Suppose we have a function y is equal to fx, and say we have to calculate this area of this shaded region. Okay, where this curve is smooth. Okay, from x is equal to a to x is equal to b. What we do? We divide it into, say, n rectangles, n number of rectangles, and we calculate the area of all these n rectangles. So we have this length as b minus a upon n, which we call it as h. Okay. So area of each rectangle, and this height is fa, then again next height is fa plus h, fa plus 2h. So we have area is the sum of fa into a, right? Fa into h, because h is this, that is breadth of the rectangle, length is fa and breadth is h. So for next rectangle, the length is a plus h and breadth is h. For third rectangle, length is fa plus 2h and the breadth is same as h. And for nth rectangle, we have length as fa plus n minus 1h. Okay, and the breadth is h itself. So we have h into fa plus h plus dot plus fa plus n minus 1h. Okay, as the sum of the area of all rectangles. So this can be written in more fashionable way like h summation fa plus rh, where r is from 1 to n minus 1. So this will give the sum of the areas of all rectangles. Okay. Now if h is here, h is b minus a upon n. So this can be written as b minus a upon n from r is equal to 1 to n minus 1 if a plus r into b minus a upon n. Okay. Now if here n tends to infinity, number of rectangle tends to infinity, then this will give the area, right, of the curve bounded by the curve x is equal to a, x is equal to b, and the x axis itself. So the value of integral a to b fx dx can be written as a form of limit when n tends to infinity, b minus a upon n, and the summation from r is equal to 1 to n minus 1 f a plus r into b minus a upon n, right? So this summation will give the value of this integral. So this definite integration is also called a limit of sum. Okay. Now, using indefinite integration, we can evaluate the definite integral. So we have fundamental theorem of integral calculus. So this theorem says that if capital Fx is antiderivative of small fx, that is, we are saying dfx upon dx is equal to fx, then we have the value of integral fx dx from x is equal to a to x is equal to b will be equal to capital Fb minus capital Fa. Okay. So what we do is we have to evaluate a definite integral. So we have to evaluate x square dx from x is equal to 1 to x is equal to 3. We find its first, what is its indefinite integral? Its indefinite integral is x cube upon 3, and we put the limit 3 and 1. So first we put f3. So the value of f3 is 3 cube upon 3, and then the value of f1 is 1 upon 3. So we have 3 cube upon 3, that means 9 minus 1 upon 3, that is 26 upon 3. So this value is 26 upon 3. Okay. So I hope you all have understood this fundamental theorem of calculus. Now we are going to lay down all the formulas for definite integral, which and then we will be solving some problems. So we have integral fx dx from a to b. We can also write it as minus of integral b to a fx dx. Okay. We have integral fx dx from a to b. Then if we change the variable from fx to t, then we can also write that as ft dt from a to b, from t a to b. Okay. We have the integral from a to b fx dx as, say, we have a, b, and say c is somewhere here. So we can write it as from a to c fx dx plus from c to b fx dx. Okay, where c lies between b and a. Okay, we have integral fx dx from a to b as integral f a plus b minus x dx from a to b. This one is very important. Okay, we will be using this truly. Fx dx from 0 to a can be written as from 0 to a by 2 fx plus f a minus x dx. Okay. Sixth one, fx dx integral from minus a to plus a can be written as fx plus f minus x integral from 0 to a dx. Fx dx integral from a to b can be written as b minus a times 0 to 1 f a plus b minus x. Not actually, we have from 0 to 1 f of b minus ax plus a. Okay, now if fx is periodic function with t as fundamental period. Then we have fx dx from a to a plus nt is equal to n times fx dx from 0 to t. Okay. Also we have from nt to mt fx dx is same as m minus n times 0 to t fx dx. We have from a plus nt to b plus mt fx dx as from a to b fx dx. Okay, so these all three are for periodic function of fundamental period t. Now we have one rule which is called Leibniz rule. If we have the derivative of the integral whose limits are also a function like this, because the value of this definite integral will be some function of x. Okay, so this can be written as g of f2x into f2x minus g of f1x into f1x. Okay, so this is called Leibniz theorem. Now we are going to look area between curves. So suppose we have a function y is equal to fx. We are wanting to find this area from a to b. Then area will be integral fx dx from a to b, modulus of that number, right? Okay. Suppose this is a function and we are now in our second case we want to find this area. Okay, from y a to b. This is the graph of y is equal to fx. So we write the function in inverse fashion, that is this function y is equal to fx can be written as x is equal to some g of y. Then we will be evaluating the area as g of y dy from a to b, modulus of that number. And if we have two curves, area between two curves, case 3, which is suppose like this, something like this and like this. If we want to find this area, okay, from a to b, this is the curve 1 is y is equal to fx and the other curve is y is equal to gx. So we have this area as fx dx from a to b modulus minus gx dx from a to b modulus. Okay, so these are, in this way we find the area between the curves. So let us have an example. Compute the area of the region bounded by the straight lines x is equal to 0, x is equal to 2 and the curves y is equal to 2 to the power x and y is equal to 2x minus x square. So first we have to draw the graphs the curve y is equal to 2 to the power x is something like this. Okay, and we have x is equal to 0 as this axis and x is equal to 2 as this axis. Okay, line y is equal to 2x minus x square. If we put x is equal to 0, we will be getting 0, right? And if we put x is equal to 2, then again we will be getting 0. So line y minus curve y is equal to 2x minus x square is something like this. So this is basically the question is asking to find this area. Okay, so we have area as the integration of 2 to the power x dx from x is equal to 0 to 2, okay, modulus minus integration of 2x minus x square dx from 0 to 2, right, modulus. Okay, so the value of integral 2 to the power x is 2 to the power x upon ln 2 from 0 to 2 minus the value of this integral is 2x x square, which is x square, and x square, which is minus x cube upon 3 from 0 to 2. Okay, this is equal to 3 upon ln 2 minus 4 upon 3. So this is the value of area, this is square units. Okay, now we will be solving some problems.